Sorry, and someone had asked for number 14? 13. So 13, this is a good one. And my confession is that this question is a little bit harder than what you guys will see. This exam was the first semester I wrote exams, and so I wasn't very experienced. So you'll see questions like this, but not quite to this level. So in this question, you have to use information from number 12 in order to solve number 13. I don't do that anymore. So yeah. There are a few times where I will have one tie into another, but they won't depend on each other, and this one kind of depended on it. So number 13, the 1 ounce bag of Doritos above. So here we have a 1 ounce bag of Doritos, and we know that that entire bag is 150 calories. So for our 1 ounce bag, all 11 chips is 150 calories. If one chip was combusted, then we're looking at 1/11 of that number of calories. So 150 calories, and there are 11 chips and per bag. And what we're calculating is how many calories are in one chip. Good. 150 calories per bag. One bag has 11 chips. So there's going to be, yikes. $13.63 calories. And notice that it's a big C, so it's actually kilocalories. If that chip was combusted in a bomb calorimeter containing 1.20 times 10 to the third grams of water, what would the temperature change of the water be? So we're still going to use this equation here. Heat equals mc delta T. In the problem, we have 1.20 times 10 to the third grams, and that's going to be equal to our mass. We know that the specific heat is 1.00 calories per gram degree Celsius. And I've written it like this just so that it's easy for me to see where the units are. So what units are in the numerator and what units are in the denominator. Again, because there was too many times when I was an undergrad where my units saved me in solving a problem. And then we don't know the change in temperature. That's what we're trying to find. And our heat we calculated here. And I'm going to convert that to little calories because my specific heat is in little calories. And there are 1,000 calories, little calories, in one big calorie. Hopefully I've done that right. So now we can plug in our numbers. This number looks strange to me. Is that what you guys calculated? Okay. And then I'm going to multiply these two numbers together, and then I'm going to divide by this number so that I can get delta t by itself. 1.2 times 10 to the 3 times 1 is simply 1.2 times 10 to the third. Grams cancel, so I'm left with calories per degree Celsius. And again, now I'm going to divide by that. If I have a unit that's in the denominator of my denominator, then it becomes the numerator. So whatever this comes out to be, my units will be degrees Celsius. And that's good because I'm looking for a change in temperature, so it should be units of temperature. And I get 11.36. Sig figs, this really has 2 sig figs. And so I would and that has 3, so I would want 2 sig figs, 11 degrees Celsius. I'm pretty sure this answer gives in, nope, 2 sig figs, good. So the answer should be A. It's, again, this is, you guys wouldn't see that first conversion. If I'm testing you on a subject, I try to just test you on that subject and not multiple subjects. There are a few more difficult questions where I will have you do a conversion and plug it into an equation. But for most of the questions, like I would just have you showing me that you know how to use that equation and plug in the variables. So probably one of the best problem-solving techniques you can have is first figure out what you're trying to identify and then label all of your variables. Once you have all your variables labeled, you can see what information is missing. And then ask yourself, how are you going to find that? 20, which number did you want to see from Michelle's exam? 27. So 27, 125 calories of heat are added to 5 grams of ethanol at 27 degrees Celsius. Notice I've crossed this off because it's not important, but we'll get there. And then C equals 0.581 calories per gram degree Celsius. What is the final temperature? This is a doozy. It's a good one. Discriminator. So we have, again, we're trying to find the final temperature. I know that my change in temperature is my final temperature minus my initial temperature. And I also know that heat equals mc delta T. And now I just have to go through the problem and identify variables. So 125 calories, heat is going to be equal to 125 calories. And then 5, that was weird. And then C is my specific heat. And C is equal to 0.581 calories per gram degree Celsius. Oh, no, we definitely need that 27 degrees. 27 degrees Celsius is our TI. So I'm going to break this down into 2 problems. First, I'm going to solve for delta T, and then I can take this delta T, whatever I find for delta T, plug it in here, and then solve for my TF. I'll have to add 27 to both sides. But let's first find delta T. So heat is equal to mc delta T. I'm going to divide both sides by mc. So I get delta T is equal to heat over MC. Which is equal to 125 calories divided by 5 grams times 0.0581 calories per gram degree Celsius. So my units of gram cancel, calorie cancel. I've got degree Celsius in the denominator of the denominator, so again, it'll be the numerator. And that's the only units I'm left with. If I take 5 times 0.581, I get 2.905. So I'm going to take 125 and divide it by 2.905. And I end up with 43.03 degrees Celsius for my delta T. And now I'm going to take this and again, to get TF by itself, I'll add 27 degrees Celsius to both sides. Would you expect the temperature to be higher? If you have your burning food item underneath the water, you would expect that water to absorb the energy and the temp should go up. So yes, it makes sense. Yeah?
I just had a question on another one. I didn't know.
Yep. Yep.
On number 12 on yours, I got there an answer about 6.28 times 10 to the fifth, but I thought since, like for 6.
You would be right. 6.3.
Okay.
Yeah.
Is that the right answer then?
Yeah.
Okay, because my answer said.
6.28.
Yeah.
Yep.
So I was like,
Yeah.
Okay.
No, sig figs, you would have 6.3.
So that would be the correct answer?
Yep.
Okay.
Yes. So right here, this was our change in temperature. And so then we took that up here. And no, you're fine. You guys want to see another one? Yeah. Yeah. So what you want to know is you want to know that big C calories is equal to kilocalories. Which means 1 calorie with a big C is equal to 1,000 little calories. We just don't like seeing the kilo in front of calories on our food stuff because we're like, crap, that's a lot of calories. So instead we just capitalize it. Yeah.
Can you do number 25 on yours then?
Mm-hmm. Great problem. Calculate the energy in joules of a photon created by the infrared LED of your television remote. So we're given the wavelength. And we want to find energy. You guys will not be given the energy equation. So you'll want to make sure to have on your note card that E equals hc over lambda. H and C will be given to you, and then we just have to convert lambda so that it matches the units for H and C. So H is Planck's constant, which is 6.626 times 10 to the minus 34th joules times seconds. C is the speed of light, which is 3.00 times 10 to the 8th meters per second. And then over that, we'll put our wavelength, which is 940 nanometers. But if you look here, that's meters. So I'm going to convert first to meters. So I'll take that 940 nanometers. And there are a trillion nanometers in a meter. You can write it, in class I wrote it as 10 to the 9th on the bottom, or you can say that there are 10 to the minus 9th meters in 1 nanometer, which is how it's shown on that table that I showed you guys in lecture. And that's going to be equal to 9.4 times 10 to the minus 7th meters. And you'll get the same answer whether you do it this way or if you do, good job, meter over 10 to the 9th nanometer. So on your guys' note card, you're going to want to, or you're going to have to memorize those 6 prefixes and what factor you have to multiply by in order to convert. So let me just write those out real fast. So make sure mega, 1 mega anything is going to be equal to 10 to the 6th of your units. So if it's a megaliter, you have 10 to the 6th liters. And then, I don't think I said giga. Kilo is the next one. So 1, and here would be your units. And those units, again, can be anything. So 1 kilometer would be equal to 10 to the 3rd meters, or 1 kiloliter would be equal to 10 to the 3rd liters. And then we have milli. There are 1,000 or 10 to the 3rd milli units in 1 of your units. So notice it switches here, and it switches here because milli, so if you think about your rulers that you have, a millimeter is a much smaller unit than a meter. And so we would expect there to be more of our smaller units. And then we have micro. And there are 10 to the 6th micrometers or microliters in 1 liter or meter. And then nano. 10 to the 9th nano whatever is equal to 1 whatever. There must be one more. Did I say centi? Okay. And then 100 centa whatever is equal to 1 whatever. So 100 centimeters equals 1 meter. So that's how I like to think about these conversions, because again, it makes more sense to me to think about how many of the smaller units make up the bigger unit. But then you can use these units like we did here. You can use those prefixes and convert your units by putting the number in front of whatever it's in front of here. So back to this problem, 9.4 times 10 to the minus 7th meters. Meters would cancel, seconds would cancel. We'd be left with joules, which is a good thing because energy's in joules. And then energy is going to be equal to 2.11 times 10 to the minus 19th joules. How many sig figs would I want? Again, in this case, 940 is just 2 sig figs, so I'd only go to 2 sig figs here. 9.1. There are only a few problems where I test you. Again, this exam, I tended to go 2 layers deep. So there are a few problems on your guys' exam where I'm explicitly testing you on sig figs. And I'll put a different number of sig figs. But for most of them where like I'm testing you on your ability to use the equation, identify the variables, and calculate things like energy, there I use the same number of sig figs. Yeah.
From the unit 1 practice problems,
Mm-hmm.
20 kilojoules, how many calories, kilocalories?
It should be 5. I think. Right here. Yeah, so if we set that up, 20.9 kilojoules, and we want to find how many calories? First, I'm going to go ahead and convert to joules. And then we have our conversion factor, which says that 1 calorie is equal to 4.184 joules. So I'm going to put 4.184 here, 1 calorie there. Plug that into a calculator. And I get 5,000.
So that's what I got.
Good.
The answer says it's
So it's a typo either here with calories, maybe big calories, or in the answer key. Should we go over the other one that has a typo? 14. So this is the practice problems. What do you guys think 14 should be? Potassium is one of the strange ones. The symbol for potassium is K. And then we put the mass number on top and the atomic number on the bottom. Potassium is 19. So 19 should go here and 40 should go on top because this is our mass number. So it should be D. If I were to ask you how many neutrons were in this atom, what would you guys say, or how would you calculate that? Yep. Yeah. Mm-hmm. Mm-hmm. Oh, strange. They've changed rounding rules since, and I think your book takes this approach. In analytical chemistry, they apply the new rounding rules where it's like if it's an odd number, you round up. If it's an even number, you round down. So that statistically, I don't know, it works out better. So let's see if odd, Robert, do you know? Is it odd you round down?
Yes,
Odd is up. Yeah. So it might be that they're following the new rounding rules. For a test, I won't do that to you. But yes, you would want to round up if it's 5 or greater and round down if it's below 5. So 12.5, you're going to round up to 13 if you're going to 2 sig figs. I can always, and did you do the give up request answer? I can always go in and adjust scores. So I don't think it's something that I can fix though, is the only thing. Yeah, I think it might just be that they're following the new rules. So, which is annoying, right? It sure would be awesome if I followed the same rules, but. What's that? So don't quote me on it. I shouldn't say because I don't know. I just know that if it's odd, you go one direction, and then if it's even, you go the opposite direction. So like if it were odd, and you're supposed to round up, which you might, sorry, Robert, will you tell me again?
You round up and then even it stays the same number as it was before.
Okay, so even you round down, odd you round up. So for 12.5, you would round up to 13, but if it were 12.6, you would round down to 12.
I can see it's the number before the 5.
The number before the 5.
So since it's even, that would round down to 12.
Oh, weird. And then if it was 13.5?
You would round up.
Okay.
Weird. It just landed in my head nicely.
Yeah. I don't know.
Statistically, because it's just probability, what it turns out to be.
So, ask me tomorrow. I'll Google it. Siri knows the answer. Yeah, what's up? Yes. On the spring exam? All these things I'm going to learn once my kid gets into middle school. Yep. Perfect. So which element, isotope, or ion? So element is just a neutral atom. Isotope is going to be one that contains a different number of neutrons, or ion. Listed below contains 35 protons, 46 neutrons, and 36 electrons. So I'm going to give you more information than you need, but that way I'm being comprehensive with everything you need to know. So the mass number is protons plus neutrons, and that's going to be equal to 35 protons plus 46 neutrons. So 1181 should be my mass number. And then the symbol, that's going to go on top. And then I can determine what symbol I'm looking at by looking at the number of protons. Protons equals the atomic number. And so for this case, since we have 35 protons, 35 will match this number here. And so I'm looking at bromine. So right now what I figured out is that much. And then I have 36 electrons. I need to compare my number of electrons with my number of protons to figure out if it's an ion. If they're equal, it won't be an ion. It'll just be a neutral atom. But I've got 35 protons, which means that I have one additional electron, and it's going to be minus one charge. And so oftentimes, like, this is going to be the only exam where you would ever even see the mass number and a charge. Most of the time we don't even include the mass number. We just write the charge on these ions. But yes, so you would want to pick A. Cool. Any questions with that? So having something on your note card where you have like symbol, mass number, which equals protons plus neutrons, and then atomic number, which equals number of protons, and then charge, which equals, gets a little tricky here. You would want to do number of protons, probably number of, yes, protons minus electrons, because then if you have more electrons, it should end up being a negative number. Protons minus electrons. And then just know your elements. How will you know them? You'll be given this exact periodic table. So then it's just mostly association, because it'll be multiple choice for you guys. So knowing that H is hydrogen, or, you know, looking through the list. There are a few tricky ones, and there are a few that, you know, start with the same letters. So like all of these. We have a lot of C ones. We also have several N ones. So knowing, you know, that this is nickel, this is neon, this is nitrogen, that's sodium. That's another strange one. Magnesium and manganese. I was telling someone earlier that one was hard for me when I was in undergrad. I always wanted manganese to be Mg, but manganese, the N comes first. So man instead of magnesium. Yeah. And then there are a few S's too. So selenium, silicon, sulfur, scandium. But again, yeah. You won't have to know any of those because we didn't talk about subshells. So no, we're not going to talk about those. 45 through 47 on Michelle's. I did not try to cram that into today's lecture, so I'm not going to ask you about subshells for this exam. But I could ask you about shells. So, and I could ask you about valence electrons. So you'll want to make sure that you know the equation to calculate the maximum number of valence electrons. You'll want to make sure that you understand that the lower shells get filled first, and then the outer shells. Yeah. If I asked you how many valence electrons were in an outer shell, you would want to know how to find that. And that's just the group number. So, yep, as you go across, 1 valence electron, 2 valence electrons, 3, 4, 5, 6, 7, 8. Yeah. You have to know 4 of the group names. I did not know chalcogens until I taught this class, so I don't think that you'll ever come across that in your life. But you'll have to know that these are the halogens, these are the noble gases, these are the alkali metals, and these are the alkaline earth. My very simple-minded way of remembering which one is the alkaline, which one is the alkaline earth, is that the alkaline earth, that's a longer name for that group, and it comes second. So the shorter name comes first, longer name comes second, right? Nothing clever there. And then we have metals over here, non-metals over here. Periods, this direction, groups, this direction. And is it elements in the same group or elements in the same period that have similar reactivity? No. 50-50 chance. Yeah, no. It's the elements in the same group. So just remember everything that belongs in the same group has the same group name. And so they behave similarly. So these guys all behave the same. These guys all behave the same, as do these. Groups are columns. Yeah. Right. So, and that's because of atomic radius. So that's the other, make sure you guys know your trends. So atomic radius, these are getting bigger. And then as you go across, that's the one that's weird. As you go across, they're actually getting smaller. And they're getting smaller because we have the same number of shells in a period, but there's more neutrons pulling those electrons in. So smaller, bigger. So overall, it gets bigger going this direction, or the size decreases going this direction, whichever. What's that? Yes, right. Then how do we relate atomic radius and ionization energy? Ionization energy, you're forming an ion. To do that, you have to remove an electron. So if it's smaller, it will have a higher ionization energy. And the bigger it is, so down over here, we're going to see elements with the lowest ionization energy. And then fluorine and helium, those have the highest ionization energies. Trying to think. We already did an energy problem. We did 2 heat problems. Do you guys remember way back when we talked about matter and how to classify matter? Good. Maybe. Should we go over it again? In my head, I have a flow chart. So my flow chart asks first, how many atoms are, and I guess I should say how many formulas do I need to describe my sample. So if it's one formula, then it's going to be pure. Two or more formulas. Mixture. So, sugar, salt, which would be C6H11O6 and NaCl. Or, like we talked about granite in class, if you see color variation throughout the sample, you're going to have different components making up those different colors. Water, sugar water, or like coffee or tea, anything that, Kool-Aid, that's all going to be a mixture because you're going to have water plus something else. So, sugar, vitamin C, anthocyanins, polyphenols, all of those crazy compounds that they tell you you should get more of, antioxidants. So, but we have to look at, if it's a mixture, we have to look at it and decide, is it the same throughout or not? If it's the same throughout, then it's homogeneous. And just like homogeneous milk looks the same throughout. And then if it's not, then it's heterogeneous. So again, we talked about wood, we talked about granite. Cinnamon sugar would be heterogeneous. Yeah. Donuts would be heterogeneous. Grapes would be heterogeneous. Oranges, heterogeneous. Orange juice. I know, right? Actually, I had a really good dinner and I'm really full, but I'm a little tired. Food is the easiest thing to think about when you're classifying things. What else? I should have been a chef. No. Okay. And then pure compounds, you have to look at how many atoms make up your sample. One atom, like mercury or gold or silver or copper, these are all going to be elemental, a pure element. And then if you have multiple atoms, but still just one formula, so water, sodium chloride, potassium nitrate, sugar. That should be a 6. These are going to be compounds, but pure compounds. Pure compounds we can't separate by mechanical means or by physical means. So like orange juice, going to food again, or saturated salt water, if you filter out the solid part of that, then, that's not a good example, but it would become homogeneous rather than heterogeneous.
Could you use an egg and salt? Because technically you're separating them.
That would be a heterogeneous mixture. Yep. But yeah, pure compounds, you can't take the atoms apart. You can't separate things unless you use some sort of chemical means. Yeah.
How is NaCl a mixture but also a pure compound?
So it has to be NaCl with sugar.
Oh, I see. They're not. Okay.
Yeah. Physical and chemical transformations, i.e. physical and chemical changes. So physical, really if you know that physical changes are changes in state, so boiling, freezing, evaporating, condensing, sublimating, or deposition. If it's not one of those, then it's probably a chemical process. And then we had chemical and physical properties. Chemical properties tell us how something reacts. So if it ignites, if it's flammable, that would be an example of a chemical property. Physical properties also like color, density. See if there's anything else I should have talked to you guys about. Rank the following colors according to wavelength. How do you guys feel about that? Roy G. Biv. Red is the lowest energy. Purple's the highest. I'll use violet. I won't use purple. Red is the lowest. Roy G. Biv, yep. Yep. So red will be the lowest, and then violet's the highest. So as you say that, Roy G. Biv, it increases in energy that way. Yep. I think we've covered pretty much everything. You guys know 2n squared. We had that eye clicker on Bohr's model of the atom, where we talked about Rutherford's model. I don't remember if I asked a question. I know I have in the past. Usually I stick with Rutherford if I ask a question about the different models of the atom. Rutherford's model is the planetary model, nucleus in the center, electrons orbiting around. Electrons exist at discrete energy levels. I think that's pretty much it. Do you guys have any other questions about any of the exam stuff? Conversions, my best tip for you is to just write your units in and make sure they cancel. I know that you'll be taking the exam and you're not going to want to write the units in because you feel crunched for time. I took the exam and it took me 16 minutes, but that's how it's supposed to be because I wrote the exam and I also, I've taught the class a few times. So they say a factor of 3, so you guys should be okay. Wait for it. Third exam. Third and fourth exam are the challenge, or the real difficult ones, but equilibrium and kinetics. 26 questions. An hour to take it. It's all multiple choice. Each question is worth 4 points. So technically the exam is out of 104 points. So one will be a freebie. No. What I do is I look at the question statistics after I get the exam results back. And I know that I'm great with words. So if there's a problem where like less than 14% of the class got it right, and one of the numbers that they calculate is this, it's called a biserial. If it's less than 0.2, then I know that it wasn't a good question. So I always look at those afterward, and if I need to throw a question out, I'll throw a question out, or I'll give you guys credit for one that you missed and you shouldn't have. But yeah, that's how I do it.